In any event, there was quite a race to measure the cosmos, and it sort of starts with Tycho Brahe, who was a very famous astronomer, did most of the best measurements of his era. He was kind of a very unusual character. He had basically a family history of dueling. Many members of his family were involved in duels. He had his part of his nose cut off in a duel. But he's well remembered for, first of all, discovering a new star, which was a supernova, Tycho's supernova. And he built really large quadrant instruments to try to measure stellar parallax. But with naked eye instruments, this is basically impossible, as he found out and many other astronomers did at the time. So moving on, we get to Galileo, who of course built the first telescope and turned it on astronomical objects 400 years ago. This is the 400th anniversary of the first astronomical telescope. And of course, he's well known for many discoveries. He discovered the Jupiter's satellites, the Galilean satellites as they're called. Saturn's rings, which he noted looked like appendages on Saturn. He discovered the phases of Venus. And actually all of these, really great discoveries all favor a heliocentric cosmology. For example, the phases of Venus are much more easily explained if we're going around the Sun and Venus is also. But since he could not measure a stellar parallax, basically the question was still open as to, did the Earth go around the Sun or the Sun around the Earth? Now he made a very interesting suggestion. He suggested that the way to measure parallax, the biggest problem in parallax measurements, would be trying to measure angles in an absolute fashion. And he said instead you should try to measure differential angles between two stars. So he said you want to find pairs of stars on the sky that are very close to each other. Hope that one is very far away and one is nearby, so the nearby one would appear to move quite a bit as the Earth goes around the Sun, and the distant one would be relatively stationary. That's a very modern thought that he had. And you'll see it'll show up now over the next century or so in various efforts to measure parallax. So we move on now to Robert Hooke, who is a very famous naturalist and astronomer and many other things in England in the 1600s. He's well known for essentially developing the microscope, for Hooke's law in physics, and he was also an astronomer. And he recognized that if you wanted to measure parallax, if you wanted to measure angles very carefully to see a small shift in the position of a star, that refraction of starlight through the Earth's atmosphere was going to be a big problem. It's about a ½ degree effect if you look at a star on the horizon. So it's a huge effect compared to the parallax that you're going to be trying to detect. And so what he did is he built a telescope aimed vertically in London, cut a hole in the roof, apparently his mother's house, and a couple floors down, and built this huge vertical tube. And the idea being if you always look straight up, you'll minimize refraction and essentially have the same refraction at any time. And there's a star called Gamma Draconis, which goes overhead in London by chance. And he tried to measure the position of Gamma Draconis as a function of time as the Earth goes around the Sun. And he did make some measurements and did detect a fairly large shift. But he of course noted there were lots of problems in this telescope that he had: vibration problems, alignment problems, temperature problems. And actually at that point he became ill and never finished his observations. So it's unclear if he could have measured a stellar parallax or not. By the way, I've been trying to get a picture of people in here, so there's no picture of Robert Hooke. He was in London and in the scientific circles at the same time as Isaac Newton. They did not get along well, and it's conjectured that Isaac Newton got rid of his portrait, if there was one, after Hooke died. Scientific jealousy, back then. Okay, now we move on to James Bradley in the 1700s, and he followed Hooke's idea, trying to measure Gamma Draconis, which goes overhead in London. And he built a very nice telescope to do this, again mounted vertically. And he got a clear detection of a shift in position depending on what season he observed. And that was detected an annual motion of roughly 20 arc seconds. But if you remember that figure of parallax, you want the offset to measure parallax. The Earth has to be maximally extended in one direction or the other to get the parallax effect. He was measuring this 20 arc second shift 3 months out of phase. In other words, when the source was nearly aligned with us and the sun, or on the other side. So with the Earth, it's essentially along the same line of sight to the source, so you shouldn't get any parallax effect. And so he thought about this and apparently could not understand this for quite a length of time, probably a year or two. And he built different telescopes to try to measure it. He measured different stars. He always got this effect, in about 20 arc seconds roughly. And what he had discovered was aberration of light. That is, if you're moving, light will appear to come in a different direction. The simplest analogy is that if you're trying to catch raindrops and you have a cup, and the rain is coming in, if you're running, for example, you're going to hold the cup a little bit tipped to try to get the maximum amount of rain in there. Same thing happens with light. If you're moving, you have to change the direction, because basically as light comes down the tube of the telescope is moving. And so it'll hit the bottom at a different position than it entered. Okay, so it's a big effect, about 20 arc seconds. Turns out the way he actually is credited with discovering this was that he was on a boat, a sailboat in the Thames, and he noticed that every time they tacked, the telltale, the wind direction, seemed to change. And he couldn't believe that the wind direction would change every time they decided to tack. Thought about it for a while and realized it's just the sum of the motion of the boat and the wind, which is the same as the light and the motion of the Earth. So, he was not able to measure a stellar parallax, but he put an upper limit on it. For Gamma Draconis, he put a limit of a ½ an arc second shift when the Earth is maximally extended. Parallax units are interesting. Arc seconds, if you invert those, you get parsecs. Okay, parsec is about 3 light years, and it's 200,000 astronomical units. So a ½ an arc second limit said the stars, this Gamma Draconis, had to be at least 2 parsecs away.
And it actually is?
We'll get to that. Okay. So the story continues. We go to William Herschel, about 20 years later. He's a very famous astronomer, and he was also a very famous composer and musician. And he made very large reflecting telescopes, and his goal was to try to find as many of these pairs of stars that Galileo said would be useful to measure parallax. So he was just surveying the sky for pairs of stars. He found many. But while he was doing this, he bumped into Uranus. He became very famous instantly for discovering a new planet. About the time he was doing this, there's an English naturalist named John Michell who did a very modern statistical analysis. He looked at how many stars you could see and said if they're uniformly and randomly distributed, how often would you likely get 2 very, very close together? And he concluded that that could not happen accidentally very often. And so almost all of these double stars that Herschel was finding had to be real binaries, physically associated, gravitationally bound pairs of stars. That's a very, very good modern scientific argument back in the 18th century. And also John Michell predicted black holes. He thought about what would happen if you put so much mass in some region, and would it attract light that much? He didn't know about bending space. That light could not escape. So he and actually Laplace, French mathematician, both thought about this, about black holes in the late 1700s. Okay, now we turn to, I think, the most fascinating part of the story as we near the end, about measuring stellar parallax, and that's Joseph Fraunhofer. Now, Fraunhofer was born in a family of about 11 kids or so. He worked for a glazier. His father was a glazier. And they were very poor. They could barely make ends meet. The kids had to work making the glass and installing it. And so there was no chance he could get any education at that point. When he was 10 years old, his mother died, and shortly thereafter